Hey, in this video we're going to look at discrete order statistics and how to calculate probabilities for an order statistic, and then how to expand that and calculate all the probabilities for a given distribution. But first, let's look at some notation here. X is our original data distributed with some function. The CDF, cumulative distribution function, is as we normally define as the probability of being less than or equal to X, and where X takes on a countable number of values. Now, it can be countably infinite. It doesn't matter. We're going to set up three probabilities here that we're going to use over and over, and we're going to call them P1, P2, and P3. And P1 is the probability of being strictly less than a value. And that is the CDF minus the density by definition. And the probability that X is equal to a specific value, that's plugging the value in the density function. And the probability that we are strictly greater than X is 1 minus the CDF, or cap F. Okay? And the kth order statistic is going to be the kth largest value of a sample size of, say, n. Okay, so this next illustration, I think, is a little maybe silly, but I think it's key to understanding how to calculate these probabilities for the kth order statistic. Okay, so I'll give the two extreme cases here. So we're going to try to find the probability that yk, the kth order statistic, is less than some value x. Okay, so k being less than x, that doesn't say anything about the n minus k other order statistics bigger than yk. Okay, as an extreme case, we can have all the larger order statistics, the k plus 1, k plus 2, etc., all the way to, all the way to n, the yn. All of these can be less than the x. Okay, and that seems trivial, but that's a possibility. So now, if we look at another case, where we're trying to find the probability that yk is less than x, the other n minus k order statistics could all be greater than or equal to x. Okay, so for yk to be strictly less than that, then at most at n minus k of the values could be bigger than x. Okay, in sort of the one extreme, we have no order statistics bigger than this x, and the other extreme is that all of the order statistics bigger than yk, so that's n minus k, or that value or bigger. And then there's anything in between. And so to actually calculate the probability that yk is less than y is actually the probability that at most n minus k of the x values are bigger than or equal to x. And so it's actually a probability, and we go from 0 to n minus k. Well, what's the probability that any given value is greater than or equal to x? Okay, so if we come back up here to our probabilities, the probabilities that we are greater than or equal to x is actually P2 plus P3. So we take 1 minus the CDF plus the density, and that's the probability that any given x is greater than or equal to x. So it turns out that this probability is a binomial distribution with n, and the probability parameter is P2 plus P3. And so the probability that yk is strictly less than x is a probability that at most n minus k of the x's are greater than or equal to x. Okay, So could be 0, could be 1, could be 2, but at most nk of them are greater than this. And this silly illustration here is pretty key to understanding this probability. So, well, we've determined that it's a binomial with this parameter P2 plus P3, and we're summing from n to, or 0 to n minus k. And then n1 minus P2 plus P3 is P1. Okay, and you can do that on your own. So now, that's the probability that yk is strictly less than x. Now, if we wanted to find the probability that yk is less than or equal to x, so this yk could be x or it could be less than that. And then, so the two extreme cases that all the larger order statistics are right on this x. So there's 0 of them strictly greater than x. And then the opposite extreme, that let's say yk is here, or it could be less, but the other order statistics, at most of them, n minus k are strictly greater than x. Okay, and you might ask why we're doing that, and that'll become apparent in a minute. So the probability that yk is less than or equal to x is the probability that at most n minus k of the x's are strictly greater than x. Well, to be strictly greater than x, that is that P3 above this one right here. So it turns out that it's a binomial, and we're summing from 0 to n minus k of this. So this is the probability of yk being strictly less than x. Okay, so now if we take the difference here of these two probabilities of being less than or equal to x and less than x, well, that's the probability of equaling x. So this is how we're going to create probabilities for the kth order statistic. And then we can sum over all possible x's, and then we can find the density. And then to this difference is this right here. And we could program this in R or any other package, but I'm going to illustrate it in R. And then it's quite easy, because once it's programmed, then you click a button and away we go. But there's a slightly more efficient way to do this, and there's a lot of sums. If n is large, and then you're having to repeat, calculating these CDFs and densities, I'm going to show you how I'm going to end up doing it in R. So here, I'll put a link in the description. There's on this video where I illustrate that the sum of binomials can be rewritten as an incomplete beta function. And so this is a CDF function in R, where we just plug in, we go from 0 to P2 plus P3. Okay, and then the notation for that is I, P2, P3, and then here's the beta parameters, for there. And there'll be a video in the description. But this isn't quite what we want. Okay, we want to the bottom half of this sum, from 0 to n minus k, not n minus k plus 1 to n. So we want the 1 minus this. Okay, and then it's a quick algebra, U substitution, to show that 1 minus this incomplete beta, you can rewrite it as an incomplete beta. Instead of parameter P2 and P3, it's 1 minus P2, P3, and you switch the alpha and the beta parameters in the incomplete beta. Well, and this 1 minus P2, P3 is actually P1. Okay, so our probabilities, I'm not sure if I had that in the video, but the 1 minus the incomplete beta can be written as a new incomplete beta, where you take 1 minus that, and then you switch the alpha and the beta. And the reason that is appropriate is the probability that we're strictly less than x, yk is less than x, is the sum from 0 to n minus k, which is this incomplete beta, which the 1 minus p2, p3 is just p1. And that's the CDF function of a beta in R. So that is very fast to calculate. And then to be less than or equal to x, we can show that it's an incomplete beta function, p1 and p2, and plug that in. And so we just take the difference of these two incomplete beta functions, and then that's the probability of yk equaling an x. Okay, so this we can use R's built-in functions to quickly calculate the distribution for discrete order statistics, and it's pretty straightforward and easy. And so let me illustrate that in R. Okay, here we're in R. We're on a Linux-based machine using the Ubuntu operating system, and we're in RK ward. We're going to calculate the kth order statistics and the probabilities of that kth order statistic, taking on specific values. So we'll assume first that our data follows a binomial, which is discrete, and we're going to calculate this function PMF yk binomial. So it's a kth order statistic using a binomial, and we're going to use the difference of two incomplete betas. And when incomplete betas means CDF of a beta distribution. And so this right here would be P1 plus P2. If you want to rewind the video, you can. And then it's the alpha parameters K, and the beta is this. And then here is an incomplete beta using P1 right here, and for the value we just take that difference. So let's add that function to R, and now we're going to illustrate it with a simple example. So we have a binomial with 22, and the parameter is 0.33, and we are going to so the x values that it can take on are 0 to 22, which is this, and we're going to create an empty vector y, which we're going to calculate the probabilities. So we're going to do this for each of the x values, and we're going to calculate the probability of each of those events happening. And we're going to do it for the first order statistic, and these are the x values that it takes on, and this is our sample size of 10. And then these are the binomial parameters, so 22 and 0.33. So let's do this, and then let's plot it. And so this is the exact distribution of the first order statistic when our data is a binomial 22.33. This is it. That's the exact distribution. So let's illustrate it for the third order statistic, and do the same thing. And then you can kind of see that the third order statistic, the distribution shifted from down around here to here. And the crazy thing is we can do this for any order statistic we want. There's the sixth order statistic. Then now let's do it for the maximum, the 10th order statistic. This is the exact distribution. And it's so easy to calculate with just this function here. But the nice thing is we can do this for any discrete distribution. So we use our incomplete betas, and then instead of P binom, we use P Poisson, or P negative binomial, or P hypergeometric, and it's the same thing. It's very, very easy and straightforward. So to do a Poisson, this is the same distribution above, except we're going to use a Poisson. And in the binomial, the parameters needed were n and p, but a Poisson we need a lambda. That's what the capital L stands for. And so let's just add that function to our available functions. And then we're going to do this for a negative binomial. And negative binomial needs an n and a p also, like the binomial. And so this is what order statistics, or the kth order statistic, what value do we want to find the probability of the kth order statistic equaling, and then this is our sample size, capital N, instead of lowercase n. So we'll add this function to our available functions, and now let's do some simulations. So here we're going to calculate the exact distribution. So this is n is our sample size here, 22. D is going to be our, my guess is I put degrees of freedom, but that's the lambda parameter in the Poisson. And we want the 22nd order statistic out of a sample size of 22. And we're going to calculate probabilities for, say, 0 to 45, and that should be enough. So the values in y now contain the exact probabilities for the 22nd order statistic from 0 to 45. Now in this simulation, we're going to do it for 50,000 reps simulation. So what it does, it creates a matrix, and each row is a sample. So the number of columns is 22. So we want 22 columns. So row 1 is a sample of 22, and then we calculate the kth order statistic, in this case 22, and then we do that for the 50,000 rows, and then we save those values, and we're going to plot them in a histogram, and then over the top plot the exact distribution. And this 50,000 reps takes a couple seconds here, and so there it is. Now remember, the bars are the simulated values, so 50,000 reps. So we just calculate a sample size of 22, find its largest value, and then repeat it 50,000 times and plot the histogram. That's this. And then the lines and circles are the exact distributions, and our simulated values are pretty darn close. The nice thing is this could be for any values. So let's do it for the 11th order statistic, and then rep that 50,000 times. And then notice the values are lower because it's the 11th largest value in the sample, not the 22nd. And the simulated values, the bars, are very close to the exact distribution as expected. And this can be done for anything. Let's calculate the minimum, and we could change the sample size and the lambda parameter. So here's the minimum order statistic, and boom, the simulated values are very close to the exact values. So let's simulate this with the binomial distribution. So here our sample size is 22, our binomial parameters are 50 and 0.6, and we want the 22nd order statistic. So let's calculate the exact distribution and store it in y. So now y contains the from 0 to 50, the possible values that our order statistic came on, the exact probabilities for each of those. And then we do a similar approach as before. We're going to simulate this 50,000 times, and there it is. This is for a binomial, and it's pretty darn close. This could be for anything. So let's take a sample size of 101. Binomial parameter is, let's say, 50 and 0.4, and we want the 75th largest order statistic, and I'm made those up. So now let's simulate this again for 50,000 reps. Boom, that's the order statistic for the 75th largest value, and the simulated values are very close to the exact. And this can also be done for a negative binomial, and sample size of 22. There's the binomial, or the negative binomial parameters is 50 and 0.7. Let's take the 11th order statistic, simulate this 50,000 times, and then plot the exact probabilities right over the top, and it is so close. Anyway, so I find this fascinating, and I'm going to end it because I think the video is getting a little long. But this is pretty exciting to be able to calculate these so easily. If you like the video, please like it, please subscribe, and there will be more to come. Thank you.